Welcome to our lecture online. One of the most interesting applications of max-min problems has to be the principle of Fermat. The principle states that light will take the path of least time. In other words, if there's an object here that reflects light and it's being reflected by a mirror and here an image is being formed, then the path that light will take the least amount of time to get from there to there. The implications of that then is that these angles, theta 1 and theta 2, will be equal. In other words, the angle of incidence and the angle of reflection, when something is reflected off a flat mirror, those two angles should be equal to one another. And we can do that by showing that light will take the least time to get there, which means it will take the shortest path. And from that, we should be able to show that those two angles are equal. Now, theta 1 can be defined as the ratio of the opposite side to the adjacent side. So the opposite side would be this distance here, which is the distance between those 2 points, c minus x. So this is c minus x, and this point is a. So c minus x divided by a, that would be theta 1. So theta 1 should equal theta 2. So we're going to show that c minus opposite side, that's c minus x, divided by a must equal, and theta 2, that would be the opposite side, which is x, adjacent side is b, that would be x over b. Of course, we can turn those around, doesn't matter. That's what we're trying to show. So, step 1, we drew a diagram. Step 2, we need to determine what we're trying to maximize or minimize. In this case, we're trying to minimize the path length. And an equation for that would be the total path length would be equal to the sum of the two paths, L1 and L2. Say this is L1, this is L2. And L1 can be defined as the square root of the opposite side, which would be the square root of c minus x squared plus the adjacent side, which is a squared. So that would be length L1 plus length L2, that would be equal to x squared plus b squared. So this side squared plus this side squared. And since we don't have any numbers or anything like that, I think we can go ahead and use that equation. We don't need any what I would call constraints or anything like that, because we've already defined the lengths of those two. We're now ready to go to the next step, which is step 6, taking the derivative of the length, and that's going to be equal to, here we can say that is 1/2 times the derivative of what's inside, which is 2 times c minus x to the first power times the derivative of what's inside, which is minus 1. And I'm wondering if maybe I should just multiply that out first. I think I'll go ahead and do that instead. Let me go ahead and multiply that. That may make it for a cleaner equation. Let's try that. Okay. All right, so L is equal to the square root of, so this becomes c squared minus 2cx plus x squared plus a squared plus x squared plus b squared. I think that's better to work like that. And now we're going to take the derivative. L prime is equal to 1/2 times the derivative of what's inside. That's a constant. This would be minus 2c plus 2x divided by the square root of this, which would be c squared minus 2cx plus x squared plus a squared. And plus 1/2 times the derivative of what's inside, which is 2x, divided by the square root of x squared plus b squared. And of course, now we're going to set that equal to 0. So step 7, set L prime equal to 0 and solve for x. Because in this case, x is the only unknown number that will determine where the light beam will hit the mirror, and that will then allow us to determine the angles. So let's go ahead and do that. Set that equal to 0. So if 0 is equal to, and this 1/2 will cancel out with those 2's, so we end up with minus c plus x divided by the square root of c squared minus 2cx plus x squared plus a squared. And then here we have plus x divided by the square root of x squared plus a squared. And that should be not a squared, but b squared. All right. Now we're going to separate those two. When I do, I bring this to the other side. The sign will change. It will then be x plus, that will be c minus x. And I'm going to square both sides. So I have c minus x quantity squared divided by c squared minus 2cx plus x squared plus a squared is equal to, on the right side we have x squared divided by x squared plus b squared. So again, I move this to the left side, the equal sign. This became plus, that became minus. I square the top and the bottom, square top and the bottom. And of course, c minus x quantity squared, that will be c squared minus 2cx plus x squared. So let's go ahead and just simply multiply that out as well. All right, now that we have that, we can cross multiply and try to simplify things as much as possible. On the left side, multiplying this times this, we get c squared x squared minus 2c x cubed plus x to the fourth. Now multiplying the b times that, plus c squared b squared minus 2cb squared x and plus b squared x squared. So that's multiplying x squared plus b squared times this numerator. We set that equal to the product of this times this, which is c squared x squared minus 2cx cubed plus x to the fourth and plus a squared x squared. Remember, we're trying to show that this is true. We're a long ways from that apparently, right? But let's see if we can simplify some things here. We have a c squared x squared on the left side and the right side. That cancels. A minus 2cx cubed, a minus 2cx cubed, that cancels. An x to the fourth and an x to the fourth. And all of a sudden, it doesn't look that bad anymore. So now we can go ahead and we have here, this, and this. This is x to the first power, x squared. Let's move everything over to one side. So that means we have 0 is equal to, if I move this to the left side, or to the right side, end up with a squared minus b squared times x squared. So move this to that side. Then I have this term right here that becomes plus 2cb squared x. And move this to the left side, that becomes minus c squared b squared. So now I have a quadratic equation, which I can solve for x. Hopefully things will simplify enough where I can solve this. Let's try that. So we have x is equal to minus b, which is minus 2cb squared, plus or minus the square root of this quantity squared, which is 4c squared b to the fourth, minus 4 times a, which is a squared minus b squared, times c, that makes it a positive, that would be c squared b squared. The whole thing divided by 2a, which would be 2 times a squared minus b squared. All right, when I multiply this out, I have a 4c squared b squared, b to the fourth. When I multiply this out, I have 4 or minus 4b squared, or minus 4c squared b to the fourth, and then I have the only term left over is that. So this will cancel out with that part, and I'm left with x is equal to minus 2cb squared plus or minus the square root of 4a squared c squared b squared. And luckily, I can go ahead and take the square root of that. So let's see here, this cancels out that, 4a squared, b squared, c squared, and the whole thing divided by 2 times a squared minus b squared. Okay, simplifying that even further, this becomes equal to minus 2cb squared plus or minus the square root of that, which gives me 2abc divided by 2 times a plus b times a minus b when I factor out the denominator. And then if I factor out what I can from the numerator, which is a 2, a b, and a c, so this is equal to, if I factor out, and by the way, the only option I have is to use the positive because that will give me a negative answer for x. That is not a practical answer, so the only thing would be a negative here and a positive there. So I'm going to factor out a negative 2, b, and c. And when I do that, I'm left with 2bc. I'm left with a b here. And I factor out the negative. And I have to get rid of this negative here. And so factor negative, this becomes negative as well. So that would be 2bc, and I'm left with an a, minus a, all divided by 2a plus b, a minus b. And since I can apply this negative here to get rid of that and get rid of that, so this negative cancels out this and this. And then the 2's cancel. I'm left with x is equal to bc divided by a plus b. So now that I have the answer for x, which tells me where the light is supposed to be reflecting off the mirror relative to this position right here, and I know that Fermat's principle is supposed to show that these two angles are the same, and I can do that by showing that theta 1 equals theta 2, which means c minus x over a equals x over b. Then all I need to do is plug this value for x into the x here and here, and then show that the two sides are equal to one another. So let's go ahead and do that and see what we get. And I'll be using purple so we can tell the difference because the board is getting quite full. So we have c minus x, which is bc over a plus b. The whole thing divided by a is equal to, instead of x, we write bc over a plus b divided by b. Now notice that on the right side we have a b in the numerator, and with b in the denominator, that cancels out. And I can cross multiply right here, multiply this a times here, and find the common denominator here, which means I get c times a plus b minus bc, all divided by a plus b, is equal to, when I move the a over here, I get ac divided by a plus b. And then again, you realize on both sides of the equation, I can cancel out an a plus b, so that cancels out. And then when I multiply this here on the left side, I have ca plus cb, and then this becomes minus bc equals ac, and of course cb minus bc cancels out, and then I show that on the left side I have ca, on the right side I have ac. Those are of course equal to one another, which shows that if this is the value for x, which I got when I worked through the problem, then I proved that this is indeed true, and therefore those angles must be equal. Fermat came up with the idea that light must take the shortest path because it must take the path that takes the least amount of time. We've shown here using the max-min problem type of approach that to travel the shortest path, the distance where the light hits the mirror, the point x must be bc divided by a plus b. When I plug that value then into this equation, where theta 1 equals theta 2, it shows that that is indeed the case, which then proves that light is reflected off a flat mirror and that the angle of incidence equals the angle of reflection. And that's how we proved it.